My project this year is the effects of pressurizing a hydrogen fuel cell. It's a continuation from my project last year, the efficiency of hydrogen fuel cell electrolytes, where I tested different electrolytes to see if one would produce hydrogen faster than the other. Last year I was more focused on the production of the hydrogen, but this year I am focused on the utilization of the hydrogen. Even though I am focused on different things from last year, I still had to use components for my testing this year. You can see here that I tested the production rates of electrolyte solutions with from 5% up to 35% potassium hydroxide by weight. You can also see that as the concentration went up, the production rate went up. Potassium hydroxide was not one of the electrolytes that I tested last year, but it does have a higher production rate than any of the ones that I tested last year. My highest production rate that I got last year was less than 1, and my highest production rate that I tested this year was 20.41 cc's per minute, which was the production rate that I was testing. Along with the higher production rate, the potassium hydroxide also is more corrosive, and I had to do safety measures such as wearing chemical splash suits, face shields, and safety goggles. Now, when you are mixing the solution with potassium hydroxide, it has an exothermic reaction with the water. So when I was mixing it, I would stir it up real quick and then I would take it outside to cool off. And in my research of the fuel cells prior to the project, when I was still studying stuff, I found basics of fuel cells, and a fuel cell is a device that converts chemical potential energy stored in molecular bonds into electrical energy. Electrochemical energy comes from the reaction of hydrogen and oxygen converted into water. And then here you can see the membrane that the hydrogen has to travel through, and this is the fuel cell that I used, and it is a small fuel cell compared to the industrial ones. Industrial ones are generally like the size of this table or bigger, and then fuel cells can have multiple membranes, and each membrane has a voltage of about 0.7 volts. So if you have 2 membranes, you'll have 1.4 volts. If you have 3 membranes, you'll have 2.1 volts. The fuel cell that I was using had 5 membranes, so it had 3.5 volts. Last year and this year, I used this hydrogen generator apparatus that I made myself. It's based off of a Hoffman apparatus, which is used in school classes and other commercial uses, but this one is made out of common consumer plumbing parts. The way that this works is you fill it up through the pressure vent or the overflow tube with the electrolyte solution. An electrolyte is an acid, a base, or a salt, and it is mixed with water to make the solution. When you fill it up through the pressure vent tube, it flows down through here, and then it flows up through here. While you are filling it up, you have these purge valves open so that the air can escape as it is being filled up. Once you get to where it's about full, you can close the valves, and for demonstration purposes, the pressure vent tube is shorter than it was during testing, but then you would fill it up past the level of these valves, and then you would flip these valves open so that the excess air that might still be trapped in here doesn't affect your testing. Once you have it filled up, you apply a charge to the stainless steel plates that are here, and One side will have a negative charge and one side will have a positive charge. Whatever side has the negative charge is called the cathode, and whatever side has the positive charge is called the anode. And you can see here on this meter the read of the charge in those plates right now. Once those plates are charged with the electrolyte in here, it'll cause the reaction of electrolysis, where it'll split the water into hydrogen and oxygen. The hydrogen will form as little bubbles off of the cathode, and the oxygen will form as little bubbles off of the anode. When they're being formed, they will be collected here in the collection vessel on either side. Once you have both sides collected enough of hydrogen and oxygen, you can channel it through these outside valves to a hydrogen fuel cell, where it will be basically reconverted into water but create electricity in the process. And I can show you how that works with the help of the diagram right here. When the hydrogen and oxygen are flowing through the fuel cell, the hydrogen will go in on one side and the oxygen will go in on the other side. The hydrogen will want to get over to the oxygen side, but to do that it has to pass through a membrane. To pass through the membrane, the hydrogen has to lose an electron and become a positive ion. The positive ion can travel straight through the membrane, but the electron will have to travel around through a circuit producing electricity, and then it'll meet the ion on the other side, recombining to create the hydrogen atom. The hydrogen will combine with one other hydrogen and one oxygen to create water, which is the only exhaust besides heat. Now, to get the flow started when you open these valves, you have to flip open these valves real quick just to get the flow started. Then you can close them so that the density of the gases here is larger and, well, heavier, but so that more hydrogen is traveling through the membrane to the other side, which will cause a higher energy output. Now, what I was testing this year was seeing if pressurizing the system as the hydrogen and oxygen were traveling through the fuel cell, is if pressurizing it would have a higher energy output. And you can see my variables here. My independent variable was the pressure that I was applying because I was changing it, but it wasn't affected by any other variables. My control variables were my membrane material, my membrane surface area, and the temperature. And they were the control variables because I could have changed them, but I decided to keep them the same, but they weren't affected by any other variables as well. My dependent variables were my amps and my volts, which combined to be the power because that's what I was measuring. The way that I pressurized the system as it was traveling through the fuel cell was it would be running, and then I would pump this up with this hand pump that you can see here, and I would pump it up 1 psi at a time. And with the system that I have for pressurizing it, it would push down and up through here. And that was one of the safest ways that I found for this testing, so that if I did have a leak, it would not be a big spray, just a little dribble because of the way it was pressurized. For this system to be pressurized, I did test it to see I did pressure test it up to 30 psi, and I only tested it, and for testing I only went up to 15 psi, so I made sure that it was able to withstand double the pressure that I was testing at. So right now, we are making hydrogen and oxygen in our hydrogen generator. This side is the negative side called the cathode, which produces the hydrogen. The other side is the positive side called the anode, which produces the oxygen. This in the middle is our pressure release system, which will also be used to pressurize the system. This is charged by a 60-volt DC battery, and this is the negative side and that is the positive side. This cross tube back here allows the electrons to flow in between the positive and negative side, creating the electrolysis. Up here we have our valve system. This side is used for purging the air out of the collection area so that it doesn't mix with the collection of the hydrogen. And this side is used for putting the hydrogen into the fuel cell. So we have collected enough hydrogen and oxygen now that we can open these outside valves to apply them to the fuel cell. And when we do that, we'll be able to watch on the meters and also through this fan, which will be running off of it. I can see here on the meter that we're running 4.87 volts DC, and we don't have any load yet. But once we turn this on, we have 0.085 for the load. At 4 psi, 4.672. At 5 psi, 4.685. At 6 psi, 4.6. And then when I was making my test system, I had to solder my own switch to the fan so that I could turn it on and off through a switch. And then I also had to assemble the fuel cell so that I could connect it to the fan. And here are some photos of both. And then I drew out a diagram of my test system, and you can see that here on my board, and then I also have it down here. And you can see here the generator, the anode and cathode, the battery, the fuel cell, and then the fan, and then the hand pump. And those are just some of the components that I drew out. Now, here you can see my data. And you can see here that I have my pressure from 0 to 15 psi. And oh, I gotta explain one more thing. When I had the fuel cell running, I would have it connected up to a fan, and there were 2 stages that I'd had the fan on, so like 2 stages of testing. One was free running, where it was just running free, and then locked rotor, where the fan couldn't move, but the motor was still trying to move it, which is maximum load. And those were my 2 stages of testing. And you can see here that I explained that the hydrogen fuel cell would be connected to the fan, but the batteries are connected instead. And that's just for demonstration purposes, because I can't have hydrogen and oxygen and all that stuff right now. But it also is a good demonstration of how a hydrogen fuel cell is basically a refuelable battery. But back to my data here. You can see that from 0 to 15 psi, free running watts went from 0.331 watts up to 0.348 watts. And the locked rotor went up for 2.454 watts up to 2.627 watts. And so as the pressure increased, the power also increased. For the free running, there was a 5.14% increase of power, and for locked rotor, there was a 7.05% increase of power. And you can see the trends here on this graph. So there was an increase of power as the pressure went up, and you might have noticed that I started off at the beginning saying volts and amps, and then switched over to watts and power. And that's because when you have volts and amps, those can combine to create power. So if you have your volts, which is your potential energy, and your amps, which is your current flow, you can combine those to create your total power. But as the pressure went up, so did the energy output. So that did prove my hypothesis correct. And the reason that this could be very substantial in a commercial area is because I was testing it at only 15 psi when in like big industry you could test it at hundreds of psi. And then one of the reasons that I was so focused on how to make this use in a industrial or commercial level is when hydrogen fuel cells are used in real life, they're used in transportation means that are in rural or remote areas, like in oceans, in space, in deserts. Like they're used in spacecraft and big boats, and they are being studied to be used in cars too. Future work that I could do with this project could include different types of membrane material and testing the system at higher pressures. I would also like to mention that for this project I did receive some support and donations from 3 companies: Aquarius Home Services, Stolhammer Sheet Metal, and the Fuel Cell Store. I would like to thank my teachers and my industrial mentor. Thank you.